After a highly insightful beginning over the past 3 days, we continue this academic journey with a renewed enthusiasm and a shared commitment to professional growth and knowledge enhancement. Today, we are privileged to host at another expert in the field of civil engineering. It is my honor to warmly welcome Dr. Jacklin Jeke Nilling, Assistant Professor in the Department of Civil Engineering at uh, National Institute of Technology, Karnataka, Suratkal. Dr. Nilling holds a PhD in Environmental Engineering from IIT Kanpur. His research was nominated for Outstanding Thesis Award. He earned MTech and BTech from Uttaranchal Pradesh, receiving a gold medal in his MTech degree. His research focused on critical environmental concerns including seawater intrusion, groundwater contamination, climate change impact, and sustainable wastewater treatment. He has presented his work at a prestigious platforms such as Gold Medalist and International Groundwater Conference, and has honored with several Best Presentation Award. We are truly fortunate to have with us today to share his valuable insights. We warmly welcome to Dr. Jacklin J.K. Nailing and look forward to an enriching session ahead. Thank you, sir. Welcome, sir.
First of all, thank you, Dr. Anush, for having me for this program. And I am very happy to be joining the program. Should I share my screen? Am I audible, first of all?
Yes, sir. Yes, sir. Audible, sir.
So I shall share my screen.
Please, sir.
Is it visible, my
Yes, sir.
screen?
Visible, sir. Yeah, visible, sir.
So should I proceed?
Sure, sir.
Okay. Yeah. So once again, thank you for inviting me for this talk. So basically, this is the title of my talk will be towards in situ remediation of inorganic contaminants. Basically, whatever the uh, removal mechanisms that we do, most of them are ex situ mechanism of removal of inorganic contaminants. Now, how can we try to remove those contaminants in the site itself without taking out water in the aquifer itself? So that we'll try to explore. Uh, okay, so basically, if we see what is the availability of water globally, then 96.55% of the water is in ocean, which is not suitable for consumption, and mostly they are saline water. And if we see other saline water will be 9.9%. So only 2.5% of water, global water, is fit to drink. Again, out of this 2.5 percentage of fresh water, most of them are trapped in glaciers and ice caps, which is inaccessible for drinking. Groundwater constitutes around 30.1%. Okay, so 30.1% is in groundwater. Again, groundwater, not all groundwater is accessible. Out of this, only 1.2% of water is available as surface or other fresh water. Again, if we break down this surface fresh water, then most of the surface water are in the form of ground ice and permafrost. Okay, permafrost, and then again 20% of this 1.2% is in the form of lakes, and only 0.5% of 1.2% is in the form of rivers. Now we can see how significant the groundwater in the contribution for providing drinking water for consumption. Okay, so how can we tap groundwater, safe drinking groundwater? That we will see. Okay, so when we talk about groundwater, the general conception is that groundwater is underground rivers. Okay, groundwater is flowing like a river below the below the surface, ground surface, which is not correct. The correct uh, uh, definition of groundwater is that it only fills the pores of aquifer like water fills the sponge. Okay. So those pores can either have water only, or it can have water and air. So if those pores inside these aquifers, like this is aquifer and these are pores. If those pores are completely filled with water, then they are called saturated aquifers. And if they are partially filled with water and partially with air, then they are called unsaturated aquifers. Okay, this is just a highlight about how groundwater exists below the surface of the earth. Now, the geogenic contaminant in the world, which is the area that is most prevalent. So geogenic contaminant, as I mentioned, geogenic means the source is earth surface. So these contaminants are basically released from underground earth crust. Okay. Some of the common geogenic contaminants are like arsenic, fluoride, selenium, and uranium. So there are two types of basically contaminants. One is anthropogenic, which is created by human being, and another is geogenic, okay, which is geological in nature. The extent of arsenic across the world, we can see the red areas. If we focus on in India, then we see this Gangetic basin is highly contaminated with arsenic, and Indus basin is also highly contaminated with arsenic. And also the another geogenic contaminant is fluoride. Fluoride is, we can see, southern part of India and northwestern part of India. They are highly prevalent fluoride contamination. This is another map. Okay. So we will see how basically these contaminants are coming to our groundwater. As I mentioned, they are basically geogenic in nature. Means it is coming from earth itself. How is it coming to earth? It is coming to earth through volcanic eruption or tectonic plate movement or collision of tectonic plate. Because of this phenomenon, whatever contaminants was there in the earth crust will come out, and then it will be reaching water surface, river water, and this river water will carry the contaminant, and it will deposit in its basin as a sediment. So these sediments will be having high reach of contaminants such as arsenic, uranium. Some of them will infiltrate and goes inside groundwater. Again, groundwater system can be either anoxic. Anoxic means it is deprived of oxygen, or oxic, which is abundance of oxygen, high oxygen. In low oxygen, the contaminant generally exists in the form of reduced form. Let's say arsenic. Arsenic will be in the form of arsenic 3. Oxidation state is 3. But in oxic condition, when oxygen is abundant, then the contaminant will be in oxidized form. Let's say in arsenic, in case of arsenic, it will be in the form of arsenic 5. And my title itself is that my study will be based on mixed oxic condition. So mixed oxic means it is neither purely oxic nor purely anoxic. Oxic means presence of oxygen. Okay, so let us pick up one contaminant and then see how it is released in the groundwater and how can we remove it in situ, in the site itself, in the aquifer itself. So let's take an example of arsenic. Arsenic is basically, we can see it is a colorless and odorless metalloid element, and it has several health effects. The health effects can be either acute effects and chronic effects. Acute means when exposure to arsenic is for shorter duration of time. But chronic is when we have a long duration of exposure for years or for months. Okay. So when exposure is for short duration, the symptom health effects might such as burning lips or diarrhea or dehydration occurs. But in because of chronic exposure, the people who are consuming arsenic rich water, they may have cancers and they may have neurological effects, nervous system effects, and then reproductive effects can also be there. Because of this toxicity, the arsenic in groundwater, as per WHO limit, World Health Organization, is 10 microgram per liter. Above this is harmful to human being. Below this is safe. Again, we have seen a little bit about arsenic 3 and arsenic 5. Arsenic generally in groundwater exists in two forms, +3 forms and +5 forms. +3 this forms and +5 this form. This +3 is about 10 times more soluble and toxic than +5 forms. Okay, so let's understand how arsenic reaches the groundwater, and when we are pumping out groundwater, how arsenic is getting pumped out. Okay, so we'll discuss about fate, which means what happens to arsenic after it is coming out from earth crust. What happens to arsenic? That is called fate. And transport is how arsenic is moving from one medium to another medium. As we have seen earlier, that arsenic is deposited on floodplain by rivers. After carrying the arsenic, it is deposited here and it gets buried inside through these climatic conditions and geomorphological processes that cause arsenic to be buried inside. And arsenic gets absorbed on soil particles. Either it is iron oxide particles or any other particles. So these three lines means symbol for absorbed arsenic. But because of some reason, because of the change in environmental condition, the reduction of these particles cause release of arsenic into groundwater. Thereby, whatever we pump out water here will be having arsenic. This is how arsenic is getting released. Therefore, to get safe arsenic drinking water, safe drinking water, we have to go deeper inside the aquifer. Okay, these are called deep wells. So they are safe deep wells. There is another way arsenic is released is because of microbial mediation. Because of this microbial action, whatever soil is there, that reduce the reductive dissolution of the soil particles again release arsenic, and this is how we are getting arsenic in our groundwater. So this is one method, and this is another process. Okay. So apart from reductive dissolution, so how reductive dissolution occurs? Suppose we have uh, iron oxide in our soil, it has iron 3 oxide, and arsenic gets absorbed on this surface. But because of reducing condition, these soils dissolves, reduce. Iron 3 of this iron oxide will reduce to iron 2, which is highly soluble. Thereby, whatever arsenic was absorbed on its surface will get, and it comes to the groundwater. This reductive dissolution takes place in presence of organic matter. So another method is through dissolution of arsenic bearing solid. Suppose we have a arsenic containing solid such as scorodite, which is iron arsenic solid. When it dissolves, it releases iron 3 and arsenic 5. So thereby arsenic also releases. Similarly, other arsenic bearing solids. Again, competitive replacement by other coions such as phosphate and carbonate. Since they have similar charges, similar structure, chemical structure, they can displace arsenic, which are absorbed here. If they displace arsenic here, they themselves get absorbed here, then arsenic will be released in water. So apart from these geogenic sources, there are some other anthropogenic sources such as pesticides, fungicides, mining of metals. But these anthropogenic sources are not as significant as geogenic sources. Okay. So as I have mentioned, there are several method of removing arsenic from groundwater. Okay, they are basically ex situ in nature. That means we pump out arsenic, treat it outside the aquifer, design a filter, and treat it outside the aquifer. Okay, but the problem with the ex situ method is that once arsenic is removed and absorbed on filter media, what to do with that filter media? If we dump it in dump yard, then during this raining and when it come in contact with water, it will whatever arsenic is there, it will leach out, which is a bigger problem. So can we then comes in situ immobilization of contaminants techniques, potential of in situ immobilization. Can we immobilize these contaminants in the aquifer itself so that whenever we pump out water, which will be contaminants free? So that is the concept of in situ removal of contaminants. So we attempted, this work was basically done in IIT Kanpur. So this was during my doctoral work, how I have attempted. So suppose the objective is that suppose we have arsenic here in aquifer, can we pump in iron inside so that both of them combine and form scorodite, which will be now in the form of precipitate or solid, and whenever we are pumping out, those water will be free of this arsenic, because now arsenic has already converted into this solid. So to attend this batch experiment was conducted. In the batch experiment, the reactor was uh, the reactor setup was prepared, in which 3 micromolar of arsenic 5 was added and 80 micromolar of iron 2 was added. So this is in the form of iron 2. As this is a batch reactor, this is initial concentration we will be supplying. After that, samples will be collected at different time point, and then what is the behavior of arsenic, this arsenic 5 with time will be measured. The pH was maintained around 7.5, which is close to the pH of neutral drinking water. And then system matrix was 0.01 molar sodium nitrate, which is close to the ionic strength of typical groundwater. These reactors were mixed at 70 RPM, and the periodic samples were collected, filtered through 0.2 micromolar, and collected at different time points. And then these were measured for pH and or ORP using benchtop meter, and arsenic and iron in ICP-MS, iron 2 in UV-BIS spectrophotometer, and arsenic 5 and arsenic 3 speciation using IC-coupled ICP-MS. The solid that was collected at the end of the experiment, which was basically 30th day, was preserved, and samples were characterized for FESM, EDS, XRD, XPR, XPS, and HRTM. Apart from this system, 2 more systems were conducted. First is control system. They are for control system. First is arsenic control system, where there is no iron. Only 3 micromolar arsenic is there. So this is just to see what is the effect of arsenic level due to presence of iron. Similarly, iron control reactor was conducted, where there was no arsenic, only iron was there. This is just to see the effect of arsenic on the concentration of iron. Again, I repeat, this is the main reactor where we are having both arsenic and iron. This is the arsenic level with time. The first, these diamond symbols are this arsenic control, where there is no iron. We can see that there is no decrease, approximately there is no decrease in arsenic in absence of iron. But when iron was there, the arsenic concentration level decreased with time and reached below drinking water limit within 2 hours. But this dash line is drinking water limit. Within 2 hours, presence of iron has caused decrease in arsenic concentration below drinking water. This blue boxes is for main reactor, and the diamond is for arsenic control reactor. The solid that was collected at the end of the experiment was analyzed in SEM. In the main reactor, we can see peaks of arsenic in the EDS spectrum, but which was not observed in iron control reactor, because in this system there was no arsenic. The same solid was characterized in TEM to identify phases. Then there was reflections from planes of scoroidite. Scoroidite is basically iron 3, arsenic 5 solid. and lepidochloride. Lepidochloride is basically iron oxide. Sorry. The same solid was detected in XPS analysis. Now we can roughly say that the decrease in arsenic from the system was due to precipitation of scorodite and absorption of arsenic on lepidochloride. Then this is the observed data. These data were modeled considering two uptake mechanisms. The first one is precipitation is scorodite, and the second was absorption on lepidochloride surface. This is the initial system. We had initial three arsenic 5 and iron 2, and then after that only periodic samples were collected. Then general mass balance equation is this one: mass accumulation equal to mass in minus mass out plus mass generated minus mass consumed. Mass in means whatever mass is being continuously supplied. Mass out means whatever mass is being continuously taken out. Mass generated means if there is any source of arsenic in the reactor, and mass consumed is what is the mechanism that is taking up arsenic. So in this case, since this is batch reactor, mass in and mass out will be 0, and mass generated, because there is no extra arsenic is being generated, so this mass term will also be 0. Only term remaining is mass consumed because of precipitation is absorption on lepidochloride surface, iron oxide, and precipitation is scorodite. So there are two terms. One is gamma CS, which is uh, 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 absorption rate constant. That this will determine how fast absorption is taking place, kinetic of absorption. And again, in precipitation terms, Kp. Kp is scorodite precipitation rate constant. How fast the arsenic is getting precipitated is scorodite. Okay. Again, the same mass balance equation was applied for adsorbed arsenic on the lepidochloride surface. This is adsorption constant. This will tell how fast adsorption is taking place. Similarly, precipitation of chloride. Applying all these four mass balance equation. Again, fourth number mass balance equation is how arsenic iron 3, iron 2. Initially, iron was in the form of iron 2, and it is getting oxidized and forming iron 3. So how fast that formation of iron 2 to iron 3 is taking place? This is the mass balance for that. And for detail, if someone wants to understand how the process is taking place in detail, we can have a discussion anytime, like in social media or personally, we can discuss. So using these equations, two simultaneous equations were developed. And these simultaneous equations were solved simultaneously using fourth order Runge-Kutta method, optimizing gamma CS and Kp. Gamma CS is absorption rate constant, and Kp is chloride precipitation rate constant. So we can see clear the model. Solid lines are model. Symbols are major data. Blue solid line is for main reactor.
అన్ని బిల్లి వితర మార్క్స్.
And
అక్కడే మీకు గోల్డ్
diamond
మార్క్స్.
black solid line is for control reactor. Then you considering that arsenic uptake is because of precipitation as sporodite and absorption as on leptochrosite surface, the model could closely predict the uh, arsenic level. Again, pH was measured, and we can see for control reactor where there is no iron, only arsenic is there, pH is nearly unchanged. But in main reactor where both arsenic and iron are there, the pH decreased, sharply decreased initially. The reason for decrease of pH is because initially, as I mentioned, that initially iron was in the form of iron 2. This iron 2 is converted into iron 3, and this iron 3 combines with water to form lepidochloride. This is lepidochloride. So the first reaction generate one H plus, which is hydrogen ion, and second reaction generate 3 H plus ion. Total 4 H plus ion is generated from this reaction, formation of Fe2 plus to lepidochloride. So as the definition of pH is negative log of hydrogen ion concentration, more the hydrogen ion concentration, lesser will be pH. As extra 4 H plus is generated in the system, the pH will decrease with time. Okay. So with this, I would like to summarize that okay. So in the system in which both iron and arsenic were there, and iron is in high concentration, which is of elevated level, then there is two process that is removing arsenic. The number one is precipitation as chloride, which is arsenic bearing solid, and adsorption on lepidochloride. This mechanism, precipitation and adsorption. So this can be this concept, this uh, process can be used for in situ sequestration of arsenic. For example, suppose we have this is aquifer having high arsenic. Can we just inject in iron 3 through injection wells? This iron 3 will combine with arsenic in the aquifer, and they will form iron 3 arsenic 5 solid, which will be now in the form of precipitate. And by filtering whatever we pump out well here, we can get arsenic free water. Similarly, same concept can be applied for other contaminants such as fluoride, uranium, which are geogenic in nature, which are generally prevalent in aquifers. Okay. So yeah, this was all about how in situ remediation of contaminants can be performed. Is everybody with me?
Yes, sir.
Okay.
Yes,
So
sir.
let me take this opportunity, to introduce myself and our institute. This is the NITK campus. So if we go this way, then toward this way is Goa, and toward this way is Kerala. So we have a beach here, and then this is administrative building. This is Western campus, Eastern campus, and this is Western campus. So we have an ITK beach. This is Uran Festival, which is kite festival, generally held annually, conducted by students of NITK. And the NITK has several departments and centers. And let me highlight one facility, which is Central Research Facility. So if you want to visit this CRF, then this is the link. And CRF facility where all the high-tech techniques are there, characterization techniques, all the cutting-edge characterization techniques are there. So if someone wants to, you know, uh, do some testing and any kind of testing, then they can uh, book slot here and they can analyze their samples. Okay. With this, I would like to thank everyone for your kind attention. And yes, if someone wants to visit the campus, please let me know, and I should be the first person that you should contact, and I will be happy to welcome you here. Okay, thank you so much. I hope everybody got something out of this talk.
Yes, sir.
And if you have anything to discuss, then we can have the discussion.
Have any query, please ask to directly or on the chat box. Please, participants. Okay, I think no. Okay, thank you, sir. On the behalf of all the participants, I would like to extend our heartfelt gratitude for your enlightening session on toxic presence in the oxygen and arsenic and their acute and chronic health impacts. Your ability to clearly communicate complex toxicological concept made this session highly engaged and educational. We deeply appreciate the time and expertise you share with us. Thank you, sir. Your voice is, sir, not audible, sir.
Hello, am I audible now?
Yeah, 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 sir.
So yeah, once again, thank you everyone, and we will. I'll see you once again next time.
Yes, sir. Thank you, sir. Okay. Thank you, sir.